Welcome to Study Loop.
Our known values for the problem are the EMF, which is 60 volts, the resistance, 240 ohms, and the inductance of 0.16 henries. So first, we want to calculate the energy that is stored in the inductor. This energy U, we know, is equal to a half times L times I naught squared, where I naught is the peak current. And this can be written as a half times L times the EMF over R all squared. And these values are all known. So this is a half times the inductance of 0.16 henries multiplied by the EMF, which is 60 volts, divided by the total resistance of 240 ohms, and that's squared. And hence we get the energy stored in the inductor initially to be 5 times 10 to the minus 3 joules. Next, we want to calculate the rate at which the energy stored in the inductor decreases. So first, let's calculate the current I. And I is equal to the peak current, epsilon over R, times E to the minus R over L times T. And hence, the derivative of I with respect to time, di dt, is equal to minus R over L times I itself. And so from here we can see that the rate at which energy that's stored in the inductor is decreasing, dul dt, which we know is defined as I times L times di dt, which is why we calculated di dt, is equal to minus R times I squared. And this is from above epsilon squared over R times e to the minus the minus 2 into R over L times t. So that happens at a given time t. And the rate at which energy is leaving the inductor after a given time, we can calculate. So this is minus EMF squared is 60 volts squared divided by the resistance of 240 ohms times e to the minus 2, and the resistance is 240 ohms divided by the inductance is 0.16 henries, all multiplied by the time of 4 times 10 to the minus 4 seconds. And hence we get the rate at which the inductor is losing energy after the time 4 times 10 to the minus 4 seconds is minus 4.52 watts, or minus 4.52 joules per second. So next, let's calculate the rate at which this energy, or which energy is being dissipated through the resistor. So this is PR, the power through the resistor. And this is the rate at which energy, electrical energy, is being converted to thermal energy in the resistor. And we know this is defined as I squared times R. So we can rewrite this as epsilon squared over R times e to the minus 2 R over L times time t. And again, these values are known. So this is 60 volts squared divided by the resistance R of 240 ohms times e to the minus 2 into 240 divided by 0.16 multiplied by time t of 4 times 10 to the minus 4 seconds as before. And we see that this rate is the same as the rate above, 4.52 watts with a positive sign. So as energy is decreasing in the inductor, it is increasing as it is dissipated through the resistor. So finally, let's calculate the total energy that is dissipated through the resistor. So the power as a function of time, we showed above is epsilon squared over R e to the minus 2 R over L times time t. And the total energy dissipated through the resistor, UR, is equal to epsilon squared over R times the integral over 0 to infinity of e to the minus 2 R over L times t with respect to t. And if we calculate this integral, we get this to be epsilon squared over R times L over 2R. And hence we can calculate this energy since we have these values. So again, the EMF is 60 volts, and that's squared, multiplied by the inductance of 0.16 Henry, and we can see that we suppress the units, over 2 times R squared, which is 240 ohms squared. And hence we get the total energy dissipated through the resistor after a very long time is 5 times 10 to the minus 3 joules, which is the same as the answer in part A. So what this means is that during the decay of the current, all the electrical energy that is originally stored in the inductor is dissipated into the resistor.